Hello, chemists. Let's talk about atoms. An atom is the smallest indivisible particle of an element. Now, when I say particle, when I use it, I kind of use it as a generic placeholder for really small objects, such as atoms or molecules or subatomic particles. And an element, in an earlier video dealing with the introduction to the periodic table, I introduced an element as a pure substance that could not be chemically simplified into other elements. So to give you an example of something that could be chemically simplified would be something like sodium chloride, table salt. That can actually be chemically simplified into sodium and chlorine elements. So an element is a pure substance that cannot be chemically simplified into other elements. Here, with the introduction of an atom, we can also think of an element as containing the same type of atoms. So in other words, if we had a gram of chromium, well, that gram of chromium would contain all chromium atoms and no other atoms of other elements. Now I'm going to try to use a cartoon to represent the structure, at least an introductory structure of the atom. And at the very center, that dark blue sphere represents the nucleus. Now in 3 dimensions, that blue circle would be a sphere. The gray cloud that's around that, I'll explain what that is in just a second, or what I'm trying to show with that. That would also be spherical around that central nucleus. But the nucleus here is going to contain positively charged subatomic particles called protons and neutrons. Now, these protons are positively charged, meaning that's the electrostatic charge that they carry. Neutrons are neutral. In other words, they are uncharged. They do not carry an electrostatic charge. The symbol that we give to protons is either P or P+, that's superscript plus, or N for neutrons. Most of the atom's mass is contained in the nucleus. As a matter of fact, the dimensions of the nucleus are very small. They're on the order of about 1 femtometer in diameter, which is 10 to the minus 15 meters, so very, very small. And we're going to see that elements have different numbers of protons. Well, if I compare 2 different elements, they're certainly going to have different number of protons at the nucleus, and they might very well also differ in the number of neutrons at the nucleus. So the size of the nucleus is going to depend on what element that we're talking about. But in general, think about a femtometer across. Very, very small. Now, this blue volume, if it were in 3 dimensions, this would be a sphere. This, gray volume that surrounds the nucleus. This is where we have our negatively charged subatomic particles called electrons. And these electrons are occupying this spherical volume around the nucleus. And they are negatively charged. Matter of fact, we give those the symbol E with a superscript minus. Now, the size of the atom, if you looked across in terms of diameter from about here to here, typical atom size is about 100 picometers or 10 to the minus 10 meters. In other words, if you compared the size of an atom, the diameter, versus the diameter of a nucleus, that's a factor of 10 to the 5th that relates those two. In other words, an atom is about 100,000 times bigger than the nucleus itself. Now, because these electrons are going to be in some region around here, and we're going to explore really what that means, the positions of these electrons, or possible positions of these electrons, and their energies, really what that means is an atom is mostly empty space. Right? You've got this very dense nucleus in the center, and then you might have these electrons that would be in some region around that nucleus. Now, I often get questions on what does it mean to be positively charged, let's say for a proton, or negatively charged if we're talking about electrons. Well, I'm talking about electrostatic charge, meaning if I have 2 particles that have similar charge, so such as 2 positive charges, they will electrostatic repel. They will feel a force that will want to push them away. On the other hand, if I have 2 particles that have opposite charge, electrostatic charge, they will feel a force that will pull them together, or at least attempt to pull them together. I often get questions, and well, if you've got all those protons that are positively charged packed at the nucleus, well, how can they stick together? Well, that is really a function of another type of force called the strong force. We don't normally talk about the strong force in chemistry, discussed more in physics, but yes, protons would electrostatically repel, but the strong force forces them or causes them to attract and stay put at the nucleus. Now you might be wondering, where does all this knowledge come from? Well, it comes from the scientific method, making hypotheses and testing those with experimentation. Very famous experiments such as Thomson's cathode ray tube experiment that showed evidence for a negatively charged particle called an electron. Millikan's oil drop experiment that was actually used to determine the charge, the electrostatic charge on an electron. And Rutherford's experiment that showed the nucleus of an atom was small and very dense. Experiments like these have been used to develop this model for an atom. All right, well, let's talk some atomic or elemental symbols. Now, I've got my periodic table on the right. I think a good chemist is going to have, the tools of the trade would be a good calculator, access to conversion factors, and then the periodic table. And we're going to show you some of the information that you can actually glean from this table. One of the things you can get from this is the atomic number, which we give the symbol Z. What this represents is the number of protons in the nucleus. Now, this is actually going to define the element. So in other words, for instance, all carbon atoms have the same number of protons at the nucleus. You can find it directly from the periodic table. And in a neutral atom, the number of protons actually equals the number of electrons. Otherwise, if those are not equal, then that atom is going to carry a charge, and we'll refer to that as an ion, and we'll explore that in a later video. So for example, something like boron, that number 5 here, in the previous video, I was calling this the fifth element. Well, that number 5 now has a special meaning. That is the atomic number. That tells me there are 5 protons at the boron nucleus. Carbon would have 6 protons at the nucleus. Oxygen would have 8 protons at the nucleus. Argon, for instance, would have 18 protons at the nucleus. So we're going to find that the number of neutrons can vary, but if you change the number of protons in the nucleus, possibly through, let's say, radioactive decay, you will change the element. Now, another term that we can introduce here is mass number, which we give the symbol A. What this is the sum of protons and neutrons in the nucleus. So if A is the sum of protons and neutrons in the nucleus, and remember Z is the atomic number, or the number of protons at the nucleus, that difference is going to give me the number of neutrons in the nucleus. So as an example, here are some atomic symbols. Now, we have the elemental symbols, C for carbon, B for boron, O for oxygen, and AR for argon, right? Get those right from the periodic table. And if we want to know the number of protons, well, that's just the atomic number Z. And remember, that is these numbers right here, for instance. So I'll just go ahead and circle those. So in other words, we got 6 protons, 5 protons, 8 protons, and 18 protons at the nucleus. Now, what I've circled here in this atomic symbol for carbon in the lower left-hand corner is actually the atomic number. You notice in these other ones, I didn't bother listing it. And typically, though, this is the way you're going to see these atomic symbols written. It's actually redundant to write the atomic number here, simply because if you tell me we're talking about argon, from a periodic table, I can immediately get how many protons are at the nucleus. So it's kind of redundant to tell me that we're working with the element argon and then also give me the number of protons, because I can get the number of protons directly from the atomic number on the periodic table. The mass number, well, the mass number is this number in the upper left-hand corner of the atomic symbol. So I'll go ahead and write those down. So we got 12, 10, 17, and 40. Now, the number of neutrons then we said was take the mass number, which is the sum of protons and neutrons, subtract the atomic number, which is the number of protons at the nucleus, and you'll get the number of neutrons. So here are the number of neutrons, and again, that's simply taking the atomic number 12, for instance, minus 6 here, 6 protons, leaves me with 6 neutrons. A mass number of 40 minus 18 protons, the atomic number is 18, that leaves me with 22 neutrons. Now the number of electrons, in this case all of these are electrostatically neutral, and we'll show you how we'll represent this when we talk about ions in a later video. But all of these are electrostatically neutral, so the number of the number of protons has to equal the number of electrons. So for instance, if carbon has 6 protons, it better have 6 electrons, otherwise it's not going to be electrostatically neutral. So here's my symbol for electron, e to the minus. For instance, again, argon, 18 protons, it's got to have 18 electrons to be electrostatically neutral. Now, we can assign names to these, and the names you can probably guess are going to be the elemental names, carbon, boron, oxygen, and argon. But we hyphenate the actual mass number in the name as well. So for instance, this would be called carbon 12. Boron here is boron 10. Oxygen 17, and this would be argon 40. One of the reasons for doing this is, I believe I mentioned this earlier, is that the number of neutrons at the nucleus might be different at the nucleus, even for the same element, but the number of protons has to stay the same. So this leads us to isotopes. This is where we have those situations where we got different numbers of neutrons at the nucleus. So an isotope, atoms of the same element that differ in the number of neutrons. Now they're going to have the same chemical properties, but they're going to have different physical properties. And you can probably guess one of those physical properties is mass. So for instance, if I were to compare a carbon 12 atom with 12 protons and neutrons total at the nucleus versus carbon 13 with a total of 13 protons and neutrons at the nucleus, well, the carbon 13 atom is going to have larger mass. Now let's see if we can write the atomic symbols then for these 3 isotopes, carbon 12, carbon 13, carbon 14. So I pulled this from the periodic table. So here would be carbon 12. Again, I'm not going to bother writing the atomic number down here simply because if I've defined carbon, immediately you know we're talking about 6 protons at the nucleus. The atomic number would be 6. Carbon 13, remember that mass number goes in the upper left-hand corner. Carbon 14, like so. The atomic number, again, the atomic number, I guess I've already alluded to that. We get that from that number in the periodic table. All of these have 6 protons. The mass number, again, is 12, 13, or 14. We get those right from those numbers in the names of these isotopes. So 12, 13, 14. The number of neutrons then is simply the mass number minus the atomic number, or the total protons and neutrons at the nucleus minus the number of protons. So for instance, 13 minus 6, or 13 minus this 6, gives me those 7 neutrons that are at the nucleus. And the number of electrons here, they all have to be 6 electrons because in every single case I've got 6 protons at the nucleus, and I'm assuming that these atoms are electrostatically neutral. Now, if you've heard of carbon dating, well, this is actually the isotope that's used for carbon dating. Carbon-14 will actually undergo radioactive decay into nitrogen-14. What actually happens is a neutron at the nucleus decays, transforms into a proton, and releases a high-energy electron that we call a beta particle. So not all isotopes are necessarily stable. They can certainly undergo radioactive decay, and I will say these isotopes do not all occur in the same abundance. Carbon-12 is by far the most abundant isotope of carbon, followed by carbon-13. So I hope you found this video useful on atomic symbols and isotopes. Thanks for watching.